Hello, I hope you guys can hear me. Okay, so it's almost 3:30 in the morning. I didn't know I wasn't falling asleep, so I'm just gonna be doing a live stream. Uh, okay, so the last time we were talking about building these CNN modules, right? And essentially, what we were trying to do is classify some colored images, right? But this time we already built a model, and I just want to summarize this model and how it looks like. So we will just look at this code and just draw the model out, right? So firstly, the model has so the input that you have in the model is n features, right? Now that feature can be something that you give to the whole thing. I'm just gonna give you a second. Okay, better. Now let's say the feature is 5 or something, right? I'm just gonna take the n feature as 1 for this case. So you have an image that is 28 by 28. Okay, so we have an image. I'm gonna go green this time. You have an image that is 28 by 28, and you have passing it to um, the first layer. That is your convolution layer. That is basically you're doing a uh, what I would call a convolutional operation. I'm saying the first one is basically your kernel. Just going to draw the kernel like this, and right, and I'm just saying that n feature is equals to 1. Okay, so number of feature is equals to 1, so it's just one kernel, right? And cool. So what we get out of this is so this is a 3 comma 28 28. Okay, and this would be whatever the number of features is there, right? So in this case it's just 1, so 1 comma 28 comma, sorry, this is the kernel, so kernel size would be 3 comma 3, right? I shouldn't be putting this one, this is 3 comma 3, and whatever the output is gonna come out of this is a varied version of smaller, a little smaller, right, version of the CNN, and that is your again 1 comma 26 comma 26, right? Okay, and after that you have a max pooling layer. Max pooling will basically uh, bring the whole thing down, and now after the max pooling part happens, you have much smaller uh, output, and this is again 1 comma 13 comma 13, right? And we are passing it to the next convolution layer. So again it's doing the same thing, but here the input channel is 1 and output channel is also 1. So again I'm gonna take this guy. It's a different kernel, but I'll copy it here for the sake of simplicity, right? And again what you have here is going back, going back not, it's just the loop is sorry, it's a chain, right? A sequence. um, yeah, so after this what we see is uh, the shape now becomes whatever is the shape, that is 13 turns to 11 comma 11, 1 11 comma 11, and that is it. ReLU happens and ReLU doesn't change the size, but we know after softmax, after max pooling, after the max pooling part happens, you have a simple final output from the second convolution layer. That would be simply 1 comma 5 comma 5. And so now this thing is flattened, right? If this thing is flattened, so it will be 1 comma 25 actually, right? Flattening. And then this whole thing is passed to a normal network. These are 25 nodes, and according to our network, we have the FC1 is basically 25 by 50. So we are scaling it up in this case, right? In this case, we are scaling it up all the way. There's 50 of them here, 50, and then we are scaling it down to just 3. This is the final output, right? So I hope you understand the whole structure. Okay, so this session we will be more uh, inclined towards understanding what is the dropout that we have defined right here, which is defaulted to be 0. But what does it really mean to have a dropout in our system, right? So let's go through it one by one. So I'm just creating a module. Okay, let's first read out the definition of dropout, right? So dropout is basically a regularizer basically. Okay, so it prevents overfitting in our and models by forcing the model to find different ways to get the targets, or it kind of forces the model to have to it makes the training process a little hard. It sounds a little counterintuitive, like why would you want to make the training process harder? Would you not want that your training be as smooth as possible? But no, actually what happens is, if your network is big, if your network has too many nodes, if your network is deep enough, what happens is these nodes or the parameters that you have essentially learn everything about your training data set. So what happens is, as it has learned every single data point, it's not really generalizing towards the pattern in the whole data set, rather than it learns that. So we don't want that. We want a model that generalizes over the data, rather than a model that is more of a just have learned the whole training data set. So if it generalizes better, it performs better on the validation set. Okay, so the idea behind regularization is that if left unchecked, a model will try to find the easy way out. Okay, so what it does mean, so it means that it end up relying on handful of features because these features were found to be more relevant in the training set. Okay, maybe they are, maybe they are not. So it's more of a statistical fluke, right? To make the model more robust, some of the features are randomly denied to it. So it has to achieve the target in a different way. It makes training harder, but it should result in a better generalization. Okay, that is, the model should perform better when handling unseen data. Okay, now that is what we're gonna do. Basically, what we're gonna do, the whole thing is that the whole thing looks like the randomization of features used in a random forest. Like if you have learned the classical mechanics, we have the random forest algorithm, right? We randomly select a few features and pass it to the network, not network in the set, random forest. Random forest is built up of many uh, decision tree. It's an ensemble learning process, right? So you have these sampling methods of different features on also different data sets also. So I think it's called bootstrapping, right? So what you do is you take a bunch of features and pass it through one random forest. That is, you pass it to one sequence of decision trees, and it produces few results, and then the other a few other features are passed to some other decision tree, and then it does um fit on those features only. Okay, so something like that. Okay, so let's do this. So right now what we see here is the code, and we have basically the dropping model. It's a simple linear sorry, a model that is sequential model. Inside we are defining a dropout with 0 p 0.5. So p is basically your probability. Okay, yeah. So we could have just used the f dot dropout. There's one more function. If you were to just do this f dot uh, dropout, see there are dropouts there, you can have used that, but uh, it seems to have much better options than that. So we will be going through why nn was used in a little while. Okay, because we are gonna see something cool, that is how training and evaluation differs, because you don't want to do dropouts in your evaluation stage. I'll let you know. I have actually hinted you that in few session back. So uh, so you have set few. So what we have here is some spaced points, right? So this is linspace. Basically it creates equal space between 0.1 to 1.1. So you can see the first number is 0.1 and 0.2, 0.3, all the way to 1.1. We're just creating this uh, inputs. Basically this is our input to this sequential model. Okay, and we are summing it up. We are not in the sense, I'm just showing this because it will be important, something that we will be looking soon. So you have this points, okay, which will be the input to our model. So let's do this. Okay, I'm gonna keep it 44 in this case. So you have setting this random seed, as we all know, and now the model is in training set, if training mode. So it's important to keep this in training mode. Just hold that thought. Okay, since the model does not have any weight, it becomes clear that the dropout inputs not weight. Okay, so one most important point here is that dropout drops input, not weights. Input in itself is dropped out. So if I were to give you a simple, if this is a network that we have, let's say I'm creating a network here. Okay, I'm creating a new network, not in this one. If I'm creating a new network here, okay, this is how it looks. Okay, and a few more, just two layers. Okay, so what it does is randomly select few of these inputs and don't pass them. So just these inputs will be passed in a sense, if that makes sense. Okay, so the weights are not uh what do you say, deleted, but the inputs are. Okay, in this case, but in more generally I feel like that's what happening, and these weights inputs are set to 0 in the sense, we'll see that. So in this case, if we pass these spaced inputs, that in spaced point to the model, what you clearly see is that the few of the inputs are turned 0. For example, this one is 0 now, this one is also 0, this one is 0, and then this one is 0. The four of them are 0, and my p-value was 0.5. So basically it means 50% of all the values will become 0 in general sense. Okay, so what we have here is 10 points, and 4 of them have become 0. That is not 50%, but if you put different values for this one, right, 0.45, so 45 would have 1 2 1 2 3 4 5 6 of them are 0. If I say 50, you'll see 1 2 3 4 5 of them are 0. So this is like basically around 0.5% to 50% or 55 or 60% of this data set or the input will be turned to 0. Okay, so I'm going to stick with the 44th one for our purpose. So we have 4 of the input being turned to 0 because we're using a dropout layer, right? So that's what you see out of here. And if you have noticed one more thing, okay, so so each input has a 50% chance of being dropped. Okay, by chance only 4 out of 10 were actually dropped. Okay, why that happens we'll know. And one thing that you must have noticed, that is few values are being doubled. Just see, 0.2 is turned to 0.4, 0.4 is turned to 0.8, 0.6 is turned to 1.2. So you can clearly see it's been multiplied a factor of 2. And basically that what happens is you have this whole input to preserve the output, that is the sum of the whole thing, right? Essentially this is like if dropout were not given to the whole if there was no dropout in your network, you would have gotten a value, right? You want to keep that value as you want to keep the model with dropout, the value that comes out of it as close as the value that you have for the model without dropout. So you have to actually multiply the whole thing by the factor of 1 by p. In this case, as p is 0.5, it becomes 2. So by the factor of 2, I have to multiply to keep the sum around the same as the output same as for a model without the dropout. Okay, so the remaining element need to be proportionally adjusted by a factor of 1 by p, right? Cool. I hope that makes sense. So if I were to show you, you might have seen for one thing that if I do this is the output, right? If I sum this up, you can see that the number is way too high. Hold that thought why that happens. Okay, so this is how the dropout, regular connections, we have all the connections, all the inputs coming in, but in the dropout ones you have few connections that are not being made. You can clearly see few connections are not being made. Okay, so that is where how dropout works. Okay, now the you can see the factor by which every element is multiplied, so that is 2. Okay, so let's see a few things. For example, you have this, we're just creating a linear layer. We have the output and basically the weights is just 1. So essentially we have I'm just going to delete all these ones and create a new one. You have 10 of these inputs, right? And what you're doing is you're taking these 10 of these again inputs. Okay, and this is the hidden layer. Okay, so you have this hidden layer. All of them, the value is 1 for every weight and value is 1, value is 0 for all the bias. Okay, so basically the operation happening is x, that this is the operation happening, that is, then as this is 1, so it's just x. So we are just taking all of them and so basically if it was like this, x1 plus w 2x2 all the way till w10 x10, right? As we have 10 inputs, so as all these w's are 1, so we have x1 plus x2 all the way x10, which will become the sum of all the inputs, right? Essentially we are trying to find see that. Okay, so why do you need to adjust? I hope that makes sense to you. So the adjustment has a purpose of preserving the overall level of output in the particular layer that suffers the dropout. So So let's imagine that these inputs after dropping will be fed to a linear layer, and for educational purpose that all the weights are equal to 1 and biases are equal to 0. A linear layer will multiply these weights by the dropped input and sum them up. Okay, so whatever the after the dropout has happened, that is output train is the one that we got after dropping out, right? And if we pass it through, what we see is the it's 9.4, which is exactly the sum of the whole thing as well in this case, where the weights are 1 and biases are 0, and I showed you why is that. So what you clearly see is that the sum is 9.4, and it would have been half, that is 4.7, if we hadn't adjusted the factor. Okay, so you must be so why do I need to preserve the levels of the output anyways? Because you can clearly see this guy is way different. For example, if I were to take this whole code and pass actual input, what is that spaced input here, you can see this was the actual one without any dropout. This was the one after the dropout, right? You can clearly see this value is way different from this value. So why did we do the whole preservation? I don't see the point of that. So because one thing, there is no dropping in the evaluation mode. We have talked about it briefly in the past, right? That the dropout is random in nature, so it would produce slightly different prediction for the same input. You don't want that. That's like bad, So let's see our model in the evaluation mode. So if we are in the evaluation mode, eval mode, and we have the dropout layer, we are passing the space into dropout model, and we have passed it here. You can see there is no change. The exactly how the input was, it just passed through. That is the first time we have seen the difference between evaluation mode and actually the training mode. I hope that makes sense. Why don't you want dropout layers in your evaluation? Because evaluation essentially is testing your model, right? The model training is where you want to have this regularization and care about the overfitting and all the stuff. But once your model is trained, you don't want randomly some inputs being set to 0, because then every time, even if the parameters are same, you would have different outputs if we have dropouts in the evaluation state. So that's what is the point here. Okay, so you have evaluation. If we take this evaluation, that's what I did here actually. Okay, so if I pass that, you see that nothing has changed. Okay, cool. So basically this is the sum of all the inputs, because all the weights were set to 1 and no input was dropped in the evaluation stage, right? If there was no adjusting factor, the output in evaluation and training mode would be substantially different, simply because there would be more terms to add up in the evaluation mode, right? So that is what it is. So you must be still thinking this question, that is, this part after dropout is way different from this part. So that's because it's probabilistic. What if I were to set this to be 50? In that case, is in this particular seed, we see that 50% of all the data, so that is 5 of them are 0 and 5 of them are there. In that case, you can clearly see the sum, or here if I pass through the actual, see, if I pass through, it is 6.4, which is very close to 6.6, right? So this is what we say is statistical. If the data set is more, of course it's gonna be more than 10. So what happens is it kind of have the same effect. Okay, I hope that made sense. We will see seeing that. So what we're gonna do right now is create some scenarios. For example, this is a list. I'm just showing you what you're doing. We are taking we are also putting some seeds also. Okay, so just I'm gonna tell you, the whole thing that happened is that without the adjustment, the output would have been 4.7, but we got 9.4 in that case when the seed was 44, right? Which is closer. That is, without the adjustment, the output would be 4.7, which is closer to 6.6 than the adjusted 9.4. Okay, and why is that? This happens because dropping is probabilistic, and only 4 out of the 10 elements were actually dropped when the seed was 44. That was so the factor adjust for the average number of dropped elements. We set the probability to be 50%, so on average 5 elements will be dropped. By the way, if you change the seed to 50 or something, so you will have half of them being dropped. That's what we saw, right? So let's create some scenarios. So I just want to show you something, that is, we are creating it's a list comprehension, right? We are creating 10 samples, and sample is coming from P is again 0.5. You have weights again the same. You have this whole thing, dropout. This is the dropout we're passing, and then whole thing is passed to the linear layer. So you see, this is what we got. And one thing you must have seen, that everything is, every time I run this, you have a different result. So to keep the results same, what you can do is you can put this seed here. So every time this result will always be same, right? Okay, so what's today? We're gonna create 1,000 of them, and then we are essentially creating a plot. So what do we have here? We have kept the P as 0.5. We have the distribution output, that is, right now we have basically output of a situation where we have passed the input from a dropout layer. Okay, and we created 1,000 scenarios in this case. Okay, and these 1,000 scenarios are basically being plotted. So if you see there, these are the numbers that you see, right? 9.2, 2.4, 6.0. Essentially, we would have want this number to be close to 6.6. That was the actual number, if you see, right? 6.6 is the actual number if no dropouts were given. So we want our model, as I said, what is dropout doing? It's basically making the training part a little harder by asking it to find different ways to get the same answer, right? By we are dropping out few inputs or weights, whatever you call them in this sense. What essentially we are doing is basically trying to get the same answer. Okay, so now you see that the answer that we get is pretty different. Few of them are close, few of them are far away from the actual value. But if you take like thousands, that is basically 1,000 scenarios of this happening. Okay, as again dropout is probabilistic. So I'm gonna show you one thing that is basically saying that while the random seed ensures reproducibility, dropout is inherently probabilistic, meaning it's randomly drops inputs on each cell, even though the randomness is consistent due to the fixed seed. Okay, as it is probabilistic, we have a scenario where we have thousand scenario of the same thing, and if you plot them out, we see these are the sum of the adjusted outputs, and you see most of the range is from almost 0 to 12, and the mean is around 6.57. That is very much close to 6.6, and that is what we expected from our whole data set, right? In general, in average, we are getting the same value that we would have gotten if there was no dropout in the model. So that is that. And now what you see here is basically situations when we have different values of P. So here the P value is 0.1. You can clearly see the range is base shorter, and as we increase the range or the variance, in a sense, this is the variance, right? So variance is higher And essentially, if you have a p of 0.9, if that would make basically a very bad, so everyone has the same kind of probability, and most of them will become zero. So you see the zero being the most highest of them, right? So yeah, dropout not only drops some input, but due to its product's nature, produces a distribution of outputs. Okay, so in other words, the model needs to learn how to handle the distributions of value that is centered at the value of output would have if there was no dropout. Okay, so however, the choice of dropout probability determines how the spread is. That is, if we have p value higher, that is, then the variance would be higher. As the p value goes higher, the variance of the whole distribution becomes higher in this scenario. Okay, the variance of distribution of the output grows with the dropout probability. Okay, cool. I hope that makes sense. So how dropout is working, there's a simple terms. Dropout is a way of regularization. It helps your model to basically find a different way to get the same answer. And what, so once you have passed few inputs from a dropout layer, you also, it automatically adjust for by the factor of 1 by p, right? And essentially we have a situation where this output is close by to the actual output that we see. Cool. um, Give me a second. Okay, yeah, so let's talk about two-dimensional outputs. Two-dimensional outputs are two-dimensional dropouts. Yes. So can we use this dropout with our convolutional layer? Yes, we can. So that's why we have this thing called the two-dimensional um, dropouts. So here what we have is there's a specific dropout which is called the 2D um, dropout 2D. If I were to show you this, it's called nn dot dropout. You see there are 2D, 3D of them, right? We will be using this one actually. Okay, so this is the one we need because we are working with images, right? It drops out. Its dropout procedure is a bit different though. So instead of dropping individual inputs, which would be like the pixels of your image, rather it drops out filters in itself, the whole of the filter, all of the kernels, all the channels, right? So that is what's been dropped out instead of filters. And why is that? It's a pretty intuitive answer to that question. That is, let's say you have an image, you have, let's say, this image. If one of this image pixel is dropped, it becomes zero basically, right? That is your, it's blackish, but you kind of get what that color is by the neighboring, because there's a high correlation between the pixels nearby. So you don't want that in, right? You want a more robust method of regularization rather than that. So instead of dropping pixels, what you can do is you can drop a whole filter in itself, right? So that is where the power of dropout 2D happens. So randomly dropping pixel doesn't do much of regularization, okay, because adjacent pixels are strongly correlated. Okay, yeah, so what you have here is, this is the original image, this is a regular dropout, this is a two-dimensional dropout. A regular dropout, this is how it looks. A two-dimensional dropout, this is how it looks. Okay, so let's build our whole network now again, but this time we have a feature of phi. That is, you have phi of the um, five kernels, right? And that's pretty cool. So if I were to draw, only change that happens here is exactly uh, okay, this change here happening is here in this part. Now there are bunch of these guys, right? That is 5 of them are here. Okay, and because of that we have 5 of these coming out. Okay, so if I were to draw this, this will be 5 of these guys. Cool. So how would the dimension change? This would become, of course, this one is 3 by 3, but we have 5 of them, so it is 5 comma 3 by 3, and this, the output will be 5 comma 26 comma 26. Instead of 1 everywhere, it will be 5. We are playing with 5 of the images, right? uh, cool. So we have stacked this up in a sense. I hope that makes sense, right? So this is the model, the new model that we have, and we're training it. And we also brought, so just gonna go through the description. So we have created a model and a loss function and optimizer, but this time we have changed a few things. That is the CNN2 class with 5 filters and a dropout probability of 30. That is what we did here. There are 5 filters and the dropout probability is 30%, and the cross entropy is the loss. And instead of SGD, this time we are using Atom optimizer. That is a different kind of optimizer, and so Atom optimizer is apparently better because actually it uses adaptive learning rates. So each parameter in your model has a learning rate of its own, right? So if you like go dig into the if I were to actually show you that too, I can, once this training is done, I will show you. So right now actually the model parameter is too high, considering it's like over if I'm not wrong, it's around 6,823 parameters in the whole model. We can show you that too once the training is done. Okay, so what we see here is we have this Atom optimizer that's been used, and learning rate is this is actually called the Karpathy's constant from one of his blog. It's not really, it's just a joke, but this happens to be a really good learning rate, so we're just using that. Okay, hopefully that is pretty much all. Basically this time there are 5 filters, so you know for a fact that if I just show you, if you remember this one, right? This one had 2 filters giving you 2 images, then you stack them up and that becomes 1 comma 2 comma 5 comma 5. Here we have 5 of them, so it will be 1 comma 5 comma whatever is this. That is what we saw here, right? Basically one sample has 5 channels and then 26 by 26. Okay, so that is what it is. 5 channels are there, and we layer them up, stack them up one by one. I hope that makes sense. Cool. Okay. Okay. A little while because the parameter right now is 6,800, and the parameter that we had in the previous one, when we had just one kernel, it was actually 213 parameters, right? So that was pretty huge comparatively speaking. So that's why it's taking much longer than the ones that we have trained before. Okay. And you can, but one thing that you can clearly see, the loss that you see here is way lower. If I were to show you the loss, we'll compare the loss between the ones that we created before and this one. Did we actually have one here somewhere? Okay, it was in the 5th chapter, right? My bad. Okay, so we clearly have, so here the what do you say, the accuracy that we get is around 84.1%. Okay, and we will also see what is, okay, I guess done. Yeah, finally. Okay, it took almost 4 minutes to do the whole thing. I am gonna go and do few things, maybe explore the actual Atom optimizer. So I'm just gonna take this and let's say explore it a little bit, right? State CAT. um let's open it in the scrollable element here. Right. Oh, that looks insane, right? So many of the filters are there. So this is average, exponential. This is the first kernel, second, third. So what you see is for the first kernel, this is RGB. This is kernel number 1, kernel number 2 RGB, kernel number 3, kernel number 4, kernel number 5 with the RGB. Okay. What else? Then the Relu, then the softmax, they don't do anything. Again, now the next thing is the next convolution layer is the same thing. 1, 2, 3, 4, 5. Right? This is trainables in that. And now it straight up jumps to our according to our diagram, we have this is max pooling, then this was done, then we have this happens here and it's max pooling, and then straight away we have the flattening of the whole thing and passing it through the network. Here essentially we have, it's a linear layer, right? So these are the biases, by the way. These are the biases for the whole, if I'm not wrong. Yeah. And now this is 25. In that case it would have been not 25, because it would be 5 into 5 into 5. That is a big number actually. What is 5 into 5 into 5? Right. So it's 125, right? Yeah. 5 into 5 into 5. Yeah. So basically this is the number of elements would have been that big, right? And that is what we see here actually. 1, 2, 3, 4, 5 for the 5 filters. That this is basically the whole thing. This around 25 of them for the first channel, or first filters output, or first channel we can call it. This is for the second channel, this is for the third channel, this is for the fourth channel, this is for the fifth channel. And again the next layer, that is this part, we would also have few other things. 1, 2, 3, 4, 5, 6, 7. Okay, that happened for the first convolution layer, second convolution layer, right? And then the whole this is what we see is how the final output is here. Here is the final output. That is pretty cool. That is pretty cool. So you have the state of the optimizer as well. Okay, I hope that makes sense. I'm just gonna do this one thing. Maybe I can find what it really means here itself. I'm just putting this into ChatGPT and let's see what happens, right? I'm taking this here. Let's see. So we have this. This holds the state of the each parameter being optimized. It includes information like moment estimation and the number of optimization steps for each parameter. Optimized. This is basically your learning rate. Okay. as it said, Atom Optimizer has basically every parameter has their own state. Okay, so let's see. You see the step is right here, and ex average is the moment estimate. Okay, we will know what moment estimate in when we in the future sessions, right? So let's break it down. So what you see here, the state dictionary contains entries for each parameter in the model. Every key corresponds to a parameter index, and the value contains the following. This tracks the number of optimization step completed for the corresponding parameter. Okay, this means that steps of gradient updates have been applied to this parameter so far. Okay, and exponentially moving average and exponentially moving average of the square. We will know what that means. EMAG, if anyone who uh, has worked with time series data, they would know what exponentially moving average means. Uh, but basically, it's a way for getting a better optimizer. We will be looking into that when we go through what are momentums and Nesterov and RMS prop. These are all kinds of optimizers. Okay, cool. And then Adam comes in actually. So it is computed by decaying average of the past gradients to smooth out noises in the gradient updates. Okay, cool, cool. It's much okay. Example training output. Output sum for the scenario, adjust the sum due to the dropout and scaling. Okay, that's fine. We're not talking about that. Breaking down the param sections, the loading rate, betas, and weight decay. They'll do. Okay, so there are states there. Inside there are a few indexes. Exponential moving average for both, and then again for the one exponential moving and exponential moving average for the squared part. Okay, then again the index comes to 1. We have one more step that it took. All right. Cool. That is pretty cool. Just so you know, you must have seen the step as 1540. If you remember, in our whole system, we had 154 batches, right? And we are running for 10 epoch. That you can see here, 10 epoch. So basically, there, how many steps are there? 10 into 158, that is 1580. That is the number of steps that we took. Basically, it says. Cool. So for every parameter, if you have noticed, every actual weights, the parameters that we have, it also keeping track of these few things. That is your exponential moving average of gradients and exponential moving average of squared gradients. These two things have to be saved. That is what makes it much. Adam optimizers have their own states. If you are looking into LLMs, right? I'm digressing a little, but why is it very hard to store these LLMs or train these LLMs? Although even if you have like 1 GB of LLM, 1 billion parameter LLM, you would require, if it's also depends upon the floating point, how it's stored, what is the precision of the numbers that you're storing, right? On average, this 1 billion parameter, if we are using FP16, it would need around 24 GBs to actually train the whole thing. So what happens is, as you can see here clearly, these things are also stored. If you are using Adam Optimizer, what you have is these 1 billion parameters have again 1 billion of these, this one being stored, and again 1 billion of this one also being stored. So that kind of doubles and triples the whole memory that it needs to store. So optimizer state has to be also saved in the VRAM when you're using GPUs. So that's why VRAM is very important, that you have to store all these data points inside the VRAM, right? So I hope you can actually see into why is this happening. Why do we need so much of compute when you're training big models? Okay, so that is there. Of course, now all the things that we are storing is we are passing in the inputs, right? And as inputs is there, we have to store that also in the VRAM. We have to store the uh, weights, the value of weights also in the store. We have to store also this optimized state. So all these things seem to, that's why the whole size of the model becomes so much bigger than what we anticipate. Okay, cool. Hmm. Okay, let's move breaking down the. Okay, let's look at this. There's a learning rate of 0. That's what we set. There's a beta value, that for epsilon value, a few of the values that is given learning rate of the group is it, beta is, these are the exponentially decaying rate. We will know what that means, okay, soon. There's a formula that you need to know for that. And the weight decay. So weight decay, it is controlled the L2 regulation of the parameters. In this case, it's set to 0, meaning no weight decay is applied. There isn't any weight decay, right? Yeah. What else is the parameter reference? The param list includes reference to the index of the model parameters 0, 1 all the way to 7. So there are 8 modules. Okay, can I actually justify that? Let's see if I can justify all these 8 modules, right? One thing is this guy, that is your kernel, right? Kernel is there, 1. And then what else? ReLU does not matter. This is a matter. Again, here I would have another 2, I suppose. And then straight away we have 3, 4. Okay, I'm missing out something. Something is missing. Let's see if ChatGPT can help us understand this, right? Why spend time doing that when we can just pass in the model itself and ask it to help us understand these parameters, right? Can you explain the reference? Let's see, what is the parameter reference? As in, what is the numbers indicating from the model definition? Okay, let's see. To parameter state of the reference to the index of the parameter of the model. This index maps to specific learnable parameters, weights and biases. Okay, listed in order in which they appear in the model. Let's map it. Okay, the first one is, of course, the convolution. Okay, the layer has 2 sets of learner parameters. The weights, that is this guy, output. Okay, that's fine. The bias is there. So index is 1 and 0. Okay, let's go dig deeper. I'm having a lot of fun actually doing this one. So you have 0 being what? The weights of con 1. So this is the weights of the con 1, and this is the things that they store with that. Okay, the 2 things that you are storing. Then this is the bias of the whole thing. As I said, these are the bias. Then next is con 2D. This one is for the second guy, and again its weight is bias and stored here. Cool. Now 4, 5 being FC1 and FC2. Cool. 4 is being FC1. Now FC1 looks like to me here is the linear layer maps to 50 neurons. It has two sets of learnables, right? Input shape is 50, and feature, whatever feature in this case was 5 actually, right? So that's what we have here. You can see this dot, that means pretty big. You can clearly see it's 1 2 3 around 5 so it's a long one actually. This is at this point, uh 50 comma 5 comma 5 comma 5, 50 comma 5 into 5 into 50 comma uh 125, 50 comma 125. That's a huge one. Can I break this down actually? Can I actually visualize this whole thing? If I can, that would be really great, right? What was it? Optimizer, right? Optimizer cnn's dot state detect, and let's see if this is a dictionary, which it is, right? Yeah, it's a dictionary. And can I index upon, let's say, the fourth guy, right? Oh, I cannot. Maybe I have to go state, yeah, and then 4, I guess. Is this it? I think that makes it as list. This is can I go like 0? Yeah. Okay, that wiki gave you the 0th one. I want the 4th one, right? Yes, this is the same thing, right? The 4th guy. Where's the 4th guy? Yeah, here it is. Okay, you see this guy. This is exactly what I'm looking here. 4th guy being here. Let's open this up a little bit, and maybe have a split of both of them. And around, where is it? Here. Yeah. Just to tally the both things. Okay, although I have it, I do not see into it. If only there was a way. Okay, I can just do a shape on this, right? No, I have to go inside this guy. I have to go, let's say this. Yes. And now we can do a shape on this guy. Cool. Yeah, that is fascinating actually. I like this. So where were we? We were trying to find basically what all these numbers mean. Now we have 6 being the final one, that is its shape is 3 comma 50. So you have 3 of them. 3 is 1 2 and 3, and there are 50 of them. You can clearly see that happening. And again, the 7th one being the bias part for this, just 3 bias for that, right? And that is it. We have all of them being layered out, and I think this is a beautiful explanation to the whole thing. Cool. You know what, I will keep a screenshot of this one. Screenshot of this one here somewhere. Cool. Yeah, that works. I think this is beautifully done. Okay. Okay. I think that is enough for this whole live stream. Next time, or the model is trained, we will just, okay, I can just do this, the accuracy of the model, right? Accuracy is around, for the first one, only 89 of them were correct. The second one was good. Third one is also good. That is what we have. Or maybe I can go through this also, right? It's not a big deal. It's just 1 hour. I can go more than this. So let's see the effect of this regularization in the whole data set, right? So dropout layer were used for regularizing. That is, they should reduce overfitting and improve generalization. So let's see what can it that does happen or what. So you have a situation where there is no regularization whatsoever, and we're plotting both of them against each other, and you can clearly see that. So basically here you have, with the dropout is the uh, darker one, okay, not the daughter one. The daughter one is without any dropout. Although in the dropout, in the line without the dropout, that is a dash line, the training loss is really good, but you can clearly see the validation loss is much higher. That is what we expect, right? But with dropout, you see the training loss is of course a little higher, but a better validation loss, and that's how we know that the overfitting of the model has been reduced significantly. Okay, and now you have also the train loader for no dropout. In this scenario, what you see here is almost everything in the training data set is absolutely right. But if you evaluate the same model over the testing data set with no dropout, it's not that great. But with dropout, you clearly see a difference. That is, your not a lot of them in the training data set are correct, but the testing data set is much better. So the model has generalized better overall on the data set. Okay, again, this is basically the visualization of the thing, right? I think visualization we can keep it for the next sessions, because this was really cool. Okay, thank you for joining if anyone did.